A digital chess piece slides across the board, setting up a perfect play. But there is no mouse clicking and no hand moving a joystick. The player is Noland Arba, a quadriplegic who is controlling the computer using nothing but his thoughts. To understand how this is possible, we have to look at the brain's baseline biology. Even in a paralyzed patient, the brain still has roughly 86 billion neurons firing perfectly. Every time you want to move, those neurons create tiny electrical signals called action potentials, which form your thoughts and physical intentions. The problem is that the biological bridge is broken. The brain generates the command, but because the spinal cord is severed, that electrical signal hits a physical dead end. The body simply cannot receive the message. Those commands have nowhere to go, leaving a fully active mind locked completely inside an unresponsive body. Scientists have tried to bypass this spinal gap for decades using older brain-computer interfaces, but early versions relied on rigid needles that scarred soft brain tissue, and they required bulky, open wires protruding directly through the patient's skull. Competing companies tried to solve the safety issue by threading sensors through the brain's blood vessels instead. But sitting that far away from the actual neurons muffled the electrical signals, severely reducing the accuracy of the data. To restore control to these patients, the hardware requires a specific combination of traits. It must sit directly against the neurons for accuracy, while remaining entirely wireless and stable enough for long-term clinical use. Elon Musk's company Neuralink approached this biological failure as an engineering optimization problem. Their solution is a coin-sized implant called the N1 Telepathy. The hardware uses 64 flexible threads, housing over 1,000 microscopic electrodes. For scale, they're thinner than a single red blood cell, but human hands lack the precision to weave something that thin into a pulsing brain. The slightest tremor could cause massive hemorrhage. To eliminate human limitation, Neuralink designed and built the R1 robotic surgeon to automate this microscopic weaving process. The R1 uses a suite of advanced sensors to map the brain's tiny blood vessels in real time. It calculates the safest routes, dodging the vasculature, and rapidly inserts the threads into specific target regions of the brain. By removing the risk of human error from the surgery, a dangerous neurosurgical procedure is turned into a standardized, scalable engineering process. When a neuron fires an electrical spike, the adjacent microthread absorbs the raw electric field. That analog signal travels into the N1 chip, instantly decoded into binary ones and zeros. The chip wirelessly beams this data via Bluetooth, turning thought into a digital command. Neuralink proved this data pipeline worked using a macaque monkey being pager. Without ever touching a joystick, Pager successfully played video games using only the translated electrical signals from his brain. But this rapid innovation came with a severe ethical cost. Neuralink's aggressive iteration pace sparked intense animal cruelty controversies, with reports estimating over 1,500 animal deaths caused by rushed surgeries, misplaced implants, and fatal infections. The N1 chip successfully bridges the biological gap, but the hyper-accelerated timeline suggests the engineering is being optimized for a broader, non-medical horizon. Phase 1 of Neuralink represents a significant shift in clinical possibilities. Beyond restoring limb movement, future iterations aim to bypass damaged eyes entirely, feeding camera data directly into the visual cortex. While these medical breakthroughs are the current focus, Musk's long-term philosophy for this technology reaches toward a different objective: the survival of our species. Musk believes that as artificial intelligence advances at an exponential rate, unenhanced humans will inevitably be left behind. His solution is that we must actively merge with AI to keep up. This is the core of transhumanism. By establishing a high-bandwidth, two-way connection to the brain, humans could eventually communicate via telepathy, upload memories to a server, and potentially achieve digital immortality. Neuralink's endgame is to shift the technology from a medical device used to heal the sick to a consumer upgrade designed to evolve the human mind. Opening that door exposes a terrifying vulnerability. If your brain is constantly connected to a wireless network, your most private thoughts and memories can be hacked. We already deal with data breaches on our phones. Now apply that to human consciousness. Imagine a catastrophic scenario where a digital virus or piece of malware is uploaded directly into your mind. Then there are the corporate risks. Tech companies are notorious for artificially throttling old devices to force you to buy the newest model. Apply that to biology, a corporation slowing down your cognitive processing speed or injecting unskippable advertisements directly into your visual field. Beyond the individual risks, this creates a massive societal divide. How could a natural, unupgraded human ever compete for a job or resources against a wealthy class of digitally enhanced superhumans? Neuralink is beginning as a noble choice to heal the paralyzed, but in the near future, having a computer chip drilled into your skull may stop being a choice and become a mandatory biological necessity.